Well, thank you very much. So I'm the Patrick part of the Patrick team. Um, and so I just want to say a quick thanks, well, first for the organizers for really interesting competition. And also to my teammates, Matthias, Mo, and Jelka. Okay, so quick introductory slide, what the challenge is. I guess we've seen this a few times now. Like Hoxing, I also like minimizing things. So I've just written things like this. So we have this data fit term and this regularizer. Just want to minimize this as fast as possible. Okay, so our starting point, not very imaginative. We also just start with majors, and our main goal was just to see if we can learn any part of the update rule. So we just start with this majors algorithm, which I've written here. So we've seen this now, a couple of times. So the main thing I think is this preconditioner P, which is this harmonic mean of this this A transpose one and the diagonal of the Hessian of the regularizer. And so we also did some tuning of the parameters. We also reduced the number of subsets. We chose about 20. And we also applied a Gaussian filter to make this OSCM reconstruction look a bit nicer. Okay. So then when it comes to learning, okay, why is this difficult? So the first thing is there are only, a handful of data points, and each one of these are from a different scanner. So you want something that would generalize across different forward operators. So the motivation was, well, let's try and learn a very simple parameterization, whatever that could mean. So an observation is we have this majors update, we have a scalar step times by a preconditioner times by an approximate gradient. So our idea was just simply to replace this scalar step with something learned, and we chose a 3D convolution. So we just want to learn a kernel instead of having a scalar step here. So why do we choose kernels? Well, it generalizes the scalar step, just take the identity kernel. And it also includes nice local structure, which could work well. And we can use a small amount of parameters, so we chose a nice 5 by 5 by 5 kernel. So very, very small parameters. Okay, now this is a fairly dense slide. So how we train things is we just start at an iteration and just look one step ahead to learn that one kernel. Okay, so we have n training points. So each of these have their own reference image, which is provided. And we're at some current iterate xt, which we start at x0, but let's suppose we're at xt currently. We have access to this preconditioned gradient, which is from this majors preconditioner. And let's suppose we have some mask. So for each image, we're interested in a specific region. I think this may not make so much sense now, but I'll try and motivate it a bit more later. Okay, so we initialize at this identity kernel and then minimize this problem, which may look a bit complicated, but so this left part is this proposed update, the right side is this reference, and all we're doing is we try to enforce or encourage the kernel K to be such that our proposed update is close to this reference. And then we average this over the data points and also within this mask. Okay. So this top loss may look slightly long, but so if you notice this convolution is linear in the kernel K. So we can just write this as a least squares problem. So there exists linear operators Bn such that this holds at the bottom, which is it looks much more simple. So using this, you can derive the normal equations and you get a nice closed form solution for this. So we don't need unrolling, no backpropagation. It's very simple, and we just use CG to find the closed form solution. Okay, so what do we actually train on? And how do we choose these masks? Okay, so first of all, the data, we only train on 5 of the smaller data points, and just because it was quick and easy, just chose 5 of them. So we have two different submissions, which just depends on which masks we use in this loss. So the first submission was just looking at this whole object mask, so just all of the object. And the second submission was because of the way the PATRIC 2 submissions were evaluated. We tried to use a combination of different masks, so look at the whole object, the background, and different volumes of interest. Yeah. Okay. So just to try and explain the training process a bit more. So when we consider this whole object loss, so we aim to learn a single 3D kernel per iteration. So every iteration we're just learning a different kernel, which is applied to all data points. Okay. So for each data set, we initialize this x0 given by this Gaussian filtering of this OSEM reconstruction. And then starting from t equals 0, we compute all the preconditioned gradients and solve the least squares problem via CG to give us this kernel KT star. And then we update all of the different data points current reconstruction and repeat again till we learn the next kernel. And this mask at the front, this mob, is just the whole object mask. Okay, the second submission is a bit more involved. So I've listed here the different evaluation criteria. So we have two different normalized root mean square errors. So we compare current reconstruction with the reference reconstruction on different masks. So we have this whole object and the background, and these need to be less than 0.01. But we also consider this absolute error. So we look at means in different regions of interest, and this needs to be better than this threshold 0.005. So we try to make a loss that considers all of this. So in two colors here, on the left side, we consider the loss very similarly to before. It's just also including this background root mean square error. We choose the mean square error as a proxy. And then for the regions of interest, to keep this, to give us a nice least squares problem, we take this squared error of means as a proxy. But we scale them some ways, and we try to work around a good way for scaling these, but it was rather tricky. So just to note, this xn hat I should be an I as well. This is just the proposed next step. Okay, so what algorithm actually learn? So there's a caveat here. So we switch after the first epoch to a handcrafted algorithm. And this was something which was quite unusual during training. So beyond the first epoch, I found eventually that learned kernels would tend to 0. And I'm not exactly sure why this would be, but it could be a consequence of training something greedy when it's stochastic. Because, stochastic, sometimes you would expect it to increase. And yeah, it's potentially the case at that point, it doesn't find anything that it can decrease. I'm not sure. Yeah. So we use these learned preconditioners for the first epoch and then switch to a very simple handcrafted algorithm. I just chose a step size of 1.5 up to iteration 60 and then just switched to 1. So very simple. So I have some results just comparing the two different submissions. So these are two data points which were not trained on. And we see basically they perform quite similarly. There's one case where this adding in the volumes of interest make a very slight improvement. And the other case, the kernel, just this standard whole object loss is better. But pretty similar. Okay, so to conclude, what we did is the very natural thing of starting with this majors algorithm. And we proposed learning convolution kernels that change at each iteration and are not data adaptive, so that it's very simple to learn. So training was really fast, so that wasn't an issue. And we had these two submissions. but there were a few challenges. So I think the biggest issue for learning is when you change forward operators. So when we generated data from one scanner, the performance was really quite better. But yes, when we had these changing forward operators, it's not so much better. And I mentioned briefly that it was difficult to find a good weighting between the several parts of the areas of interest. Yeah. And the one issue that was unusual was that kernels became close to zero. And this didn't happen when we trained on one scanner. So it'd be a good improvement to understand why these kernels become close to zero and see if we can fix this. And I think one limitation is a very simple measures step size rule that we switched to. And maybe switching to a better step size would be quite beneficial. Yeah, so thank you.
There's an applause for you, Patrick.
Thank you very much.
Are there any questions in the room? Georg?
Can you hear me, Patrick?
Yes, I can hear you.
So you said one reason, or one potential reason why you said the kernels go to zero might be because you train on stochastic gradients. Have you tried training on full gradients and then just basically reusing the learned kernels on full gradients on your stochastic gradients?
Oh, that's a good question. Yeah, so we've tried this method on full gradients, and yeah, in that case we don't get things going to zero. But the one thing I think that locally between iterations, kernels can change quite a lot. So if you have specific information from a full gradient, I'm just thinking potentially that would it could be quite sensitive to the changes from the full gradient to the stochastic gradient, but I think that's worth a try. I think that's a really nice, seemingly quite obvious suggestion. Yeah, that's a good one. Thanks. I'll try it out.
Any other questions in the room? No? Online? Let's check. No, lots of questions for you, Julian. Well, thank you again, Patrick.
Thank you very much.